Hello everyone, how are you doing? Here's a video for week 12 in my Algebra 2A live class, solving radical functions. All right, so this week make sure you're reading through on our textbook to follow along with this video as well. You can review this video as often as you need, and then be working on the week 12 assignments, including the paper pencil assignments, the weekly quiz or test, doing all that you need to do, staying on pace with this class. This is the last video for semester A. So congratulations if you're at this point and you're almost done with the class. For week 12, here's what we're going to be learning. If I give you a radical equation, can you solve it by taking the appropriate power of both sides of the equation? We're going to talk about how to solve radical equations a lot today. We're going to determine if a solution to a radical expression is a real solution, or sometimes we can solve it and we actually get an extraneous solution. So you need to check your solutions. We're going to do operations such as adding, subtracting, multiplying, and dividing with functions, kind of the second half of what we're doing. Doing a lot with function operations. If I give you two functions, can you find the composition of them and analyze it as a new function? And finally, be able to explain how in a composition of functions, it's one function inside of another function. So kind of the first half of what we're going to do today is about solving radical equations. The second half is function operations and compositions. Here we go. So last week, we did a lot in week 11 with looking at radical functions, graphs, exponent properties, all that good stuff. This week, we're going to get more into solving them in the algebra. How do you work with radical functions? How do you find unknown values for variables? So to solve radical functions, you just need to realize that a radical is the inverse of the exponent. So what we mean by that is to solve a square root equation, for example, if I have the square root of x equals 9, well, the opposite of square rooting is taking the square of both sides. So to solve that, I would square both sides and see that x equals 81. If I want to solve a cubed root equation, guess what the opposite of or the inverse of cubing is? It's taking to the third power. So solving this equation is x would be negative 3 to the third power would be negative 27. So we solve them, what we're going to do is use the appropriate power at the right time to undo whatever radical we have. All right, let's do one together. Here we go. We've got negative 2 times the square root of x plus 4 minus 6 is equal to negative 10. We want to know what does that value of x have to be to make the equation true. We're going to solve it. All right, well, let's draw my line down. And let's start doing the algebra. Again, what I'm going to show you is how I want you guys to do this on your paper pencil problems and to practice doing by hand as well. So what we need to do, the big thing is we need to isolate the radical. I'm going to write that out here. So what I'm going to do is I'm going to get rid of that negative 2 multiplying it. I need to get rid of this minus 6 outside. Everything outside of the radical being done to it, I need to get rid of first. So we work our way backwards. I'm going to add 6 to both sides. First, minus 6 plus 6, that goes to 0. So now we've got negative 2 times the square root of x plus 4 is equal to negative 4. Next up, now I'm going to undo multiplying by negative 2. The opposite of multiplying by negative 2 is to divide both sides by negative 2. Those divide out. Now I'm left with the square root of x plus 4 is equal to positive 2. All right, now I've got my isolated radical. So the opposite of square rooting is to square both sides now. So square root, squaring, those cancel out, leaving just x plus 4 is equal to 2 squared, which is 4. And finally, we're going to subtract 4 from both sides to solve for x. So x needs to be 0. That looks like what we get for the solution. But now we've got to check it out. So let's put it back in. If x is the solution, and if I put it back in, if 0 is the solution put in for x, does it work out? Does negative 2 multiplied by 0 plus 4 minus 6 actually equal negative 10? Well, 0 plus 4 is 4. The square root of 4 is 2. So we've got negative 2 times 2 minus 6. That's negative 4 minus 6. And yes, that does equal negative 10. So it all checks out. This is a solution. All right, that's what we're doing. Solving radical functions, working with examples like that. Taking the right power at the right time once we've isolated the radical. When solving any radical equation, again, make sure to isolate the radical first. I can't stress that enough. Many of you will attempt to square both sides or cube both sides or take the fourth power both sides, but you'll do it too early or too late. You want to get just the radical on one side and then take the appropriate power. For this next example, it's going to be a little more complicated, but it's again the same process. Okay, here we are. Let's solve this equation out. So I'm going to draw my line down. Again, I need to isolate the radical, so I'm going to add x to both sides. And what do we've got? We've got the square root of 6x minus 5 is equal to x minus 10. So we got it isolated, so it's obvious now. I'm going to square both sides because I have a square root. I need to square both sides. On the left side, it's nice because all I've got left now is 6x minus 5. Square root and the squaring undid each other. But now on the right side is where this is a more complicated example. I've got x minus 10. I have to square everything on both sides. That's a binomial squared. That's x minus 10 times x minus 10. And if I use my FOIL method, first, outer, inner, last, and multiply that whole thing out, I end up with x squared minus 20x plus 100. And look at what we've got now. We have ourselves a quadratic equation to solve. I got to dip into my quadratic methods, get it equal to 0, use the quadratic formula, or try and factor it, but this is where I want to solve this thing out. All right, let's go ahead and subtract 6x from both sides and add 5 to both sides. And now we've got 0 on the left side equals x squared minus 26x plus 105. All right, I'm just going to go ahead and use the quadratic formula. A, in this case, my leading coefficient is 1x squared. B is going to be negative 26, and C is going to be 105. Got some big numbers to work with, but that's okay. So my quadratic formula, now we're going to solve this. X is going to be equal to negative b, so it's positive 26 now, plus or minus the square root of b squared, so it's 26, negative 26 squared, minus 4 times a times c. A lot of stuff under there, all divided by 2 times a. All right, let's simplify this down. So if I do everything under the square root, negative 26 squared is 676. So we've got, 26 plus or minus square root of 676 minus 420. If we do 4 times 105. All divided by 2. Well, 676 minus 420 is 256. So it's 26 plus or minus the square root of 256. All divided by 2. It's getting a little bit more simpler. And guess what? I'm going to switch colors here at this point now. The square root of 256, that's a nice number. It's just 16. So my answers, one answer is 26 plus 16 divided by 2. The other answer is 26 minus 16 divided by 2. If I simplify those out, 26 minus 16 is 10. 10 divided by 2 is 5. 5 is one solution. The other one, 26 plus 16 is 42. 42 divided by 2 is 21. So we might say, okay, look at that. If my value for x in this radical equation is 21 or 5, both of those are solutions. But what we don't know is one of these are actually an extraneous solution. We need to do some checking out here now. So let me switch to a good color. Let me get some magenta. Now watch what happens. Here's where we need to test both of these out. Let's start with 21. If I take 6 times 21 minus 5, and then take the square root of that, and then subtract 21, do we get negative 10? Well, let's calculate it out. 6 times 21 is 126. If I subtract 5, that's 121. But the square root of 121 is 11. So is 11 minus 21, what does that equal? That equals negative 10. So this solution checks out. But now let's check the same thing out with 5. If I have 6, and this time I put 5 in for x, so 6 times 5 minus 5. Square root of that minus 5. What do we get? 6 times 5 is 30. 30 minus 5 is 25. And the square root of 25 is 5. So we end up with 5 minus 5, which just equals 0. Well, that's not negative 10. So this one is not a solution. It's what we call extraneous. And this is often what happens when you're trying to solve a square root. We had to do what we did here where we square both sides. Sometimes you lose that plus or that minus solution that you originally had, and so we just check them out. But this one, 5 is our extraneous solution. It is not an actual solution to this original equation. It's a solution to this quadratic, but it's not a solution to the extra radical solution. So the only solution is x equals 21 to the original radical equation. Hopefully that makes sense on why you need to test solutions, and sometimes you can get extraneous solutions. Okay. When solving equations with rational exponents, it's again an exponent, remember, is related to a radical. We just simply take the reciprocal power of both sides and use the power of a power property. This one will be pretty easy, but let me just show you what I mean by that. So say here we go. We got 7 times x to the 3/7 power plus 9 equals 65. It's like, whoa, what does x have to be in this case? Well, let's solve it out. Same thing. I want to isolate the x, the variable, to whatever power I'm dealing with. So let's subtract 9 first. That's opposite of plus 9. So 65 minus 9 is going to be 56. And we got 7 times x to the 3/7. Now I want to get rid of that 7, so I'm going to divide both sides by 7. So x to the 3/7 power equals 8. Now what do I do at this point? Here's where I'm going to use my power of a power property. What happens if I take everything on both sides to the 7/3 power? Well, the power of a power property says you multiply the exponents. So we end up with 3 times 7 divided by 7 times 3. And there we go. We end up with x to the 21 divided by 21 power, which is just x to the first power. So x is going to equal whatever 8 to the 7/3 power is. Now this is a little ugly, but again, we have a calculator that can help us calculate this out. So let's do 8 to the power of, let's do 8 to the cube root of 8, which is 2, and then 2 to the 7th power is 128. So x is equal to 128. All right, but there you go. You can now solve quite a variety of radical functions. Some of them will be pretty straightforward. Some of them will take a little bit of time to work through and solve out. All right, we are now going to switch gears and deal with compositions of functions. So we tack a little bit of this on there. It's kind of more of an advanced topic with functions. As we're dealing with f of x and function notation, we can actually add, subtract, multiply, and divide any function together. We've done this with polynomials. We added, subtracted, multiplied, and divided polynomials together. But now we're just going to look at any function. We can realize we can add, subtract, multiply, and divide any function together. We have some of the algebraic tools to do that. So for example, here we go. We've got two functions. One of them is a parabola or quadratic function, 3x squared. The other one is a linear function, got f and g. And we're going to add f and g together, and then we're going to subtract f and g together. We know how to do this. I just want you to see the notation. When you see f plus g like this, here's what this means. It takes function f, which is 3x squared, and we're going to add to that function g, which is 8 minus x. Well, this is pretty easy to see. That's just 3x squared plus negative 1x plus 8, if I put it in the right order. But adding a function, remember, just adding polynomials together. There's my new function when I add f and g together. Now let's do f minus g. Now I've got 3x squared, but this time I'm going to subtract whatever g is. That's 8 minus x. Well, here we have to distribute the negative, and so we end up with 3x squared minus 8 plus x, and if I put it in descending order, that's 3x squared plus x minus 8. And there is my new function when I subtract f and g together. So again, don't let the notation mess you up. We know how to do this algebraically. We can take functions, we can add and subtract them together. We can also multiply and divide functions together. So let's take these two functions and do that. So f g, this is f times g, so I'm going to take 3x squared, that's function f, and multiply it by function g. And in this case, we know how to multiply two polynomials. That's going to give me 24x squared minus 3x to the third. There's my new function when I multiply with the original two functions. And finally, division, f divided by g, so we've got 3x squared divided by 8 minus x. There's not really anything I can simplify there, but if you graph that, that'll be kind of a fun, interesting function to look at. This is what we call a rational function. We have a polynomial in the numerator and a polynomial in the denominator. When we graph them, they're quite interesting. Got some good domain and range, interesting hyperbola that it looks like when you graph them. We're going to talk more about this in the second semester. There you go. We did an example of adding, subtracting, and multiplying and dividing functions together. We can do this with linear functions, polynomials. We can do this with radical functions, with square roots, or with powers. We know how to deal with those as well too. Finally, let's get into compositions of functions. This is another way to take two functions and combine them together, but it's not with adding, subtracting, multiplying, or dividing. It's combining them by essentially taking one function and fitting it inside of another function. It's a nested of functions. So remember, a function, we take something, we input it into a function. Usually, typically, we put an input value for x, we calculate it out, and we get an output value for y. Well, with compositions of functions, I'm not inputting a number in for x, I'm inputting a whole function into a function and seeing what my result is. So here's some symbols, here's what this looks like. When you see function f right here, but there's function g inside of function f. Instead of f of x, look at what we put inside there. We put a whole nother function inside. So this is what we would call a composition of f and g. And we can write it out like this with this little open circle dot thing. That means take function f, put function g inside of function f. The order does matter. So I compared it to this one over here. This is function g, but take function f and put it inside of function g. So whatever this function is, it should most likely be different than this function unless they happen to be inverse functions. Well, you'll see more of that in the reading. But when you see this notation, either with f and a little function inside of it, or when you see the open circle, that indicates you're asked to find the composition. So let's do that now. Here's my two functions. There's f, there's g. I'm going to compose them together. First, I'm going to take function f and put g inside of f. Second one, I'm going to take function g and put f inside of g. Again, keep in mind we're nesting one function inside the other. So function f of g, the composition of f and g, I'm going to take function f, which is 3x squared. But notice I'm going to leave a big space for x. So this says take whatever you're inputting in for x, square it, and then multiply by 3. But what am I going to put inside of function f is function g. So I'm going to take function g, and that 8 minus x is going to go right inside of function f. So do you see how we took function g and we put it inside of function f, and now we can simplify this thing out. This is going to be the composition. So let's do some work and simplify that out. First I need to square 8 minus x. Remember PEMDAS, you do squaring first before multiplying. So 8 minus x squared is going to be 64 minus 16x plus x squared. And now I can multiply by 3 and distribute that 3. So we end up with, if I put it in descending order, put my x values first, 3x squared minus 48x plus 192. That is the function that I get when I compose f and g together in that order. It's a nice quadratic function, right? All right, now let's do the opposite. Well, let's do the composition, but this time we're going to take function f and put it inside of function g. So let's start with function g. It says take 8 minus x, so we've got 8 minus, but instead of x, I'm going to put function f inside of it. I got to fit one function inside the other. So I'm going to take f of x, and I'm going to put that in, and f of x is 3x squared, so we've got 3x squared in place of x in my function g. All right, well, let's see what we can do to simplify this now. So we have 8 minus 3x squared. This one's a little bit easier. It's just negative 3x squared plus 8. There's not much more you can simplify that. So there, notice these are two different functions because we composed them in different orders. That's composition of functions. Combining two functions together, but we're not adding, we're not subtracting, multiplying, or dividing. We're fitting one function inside of the other. Hopefully it gives you a good couple examples about how to do that. Finally, the last bit of today is inverse functions. We've already worked with inverse functions. Adding, subtracting are inverses. Multiplying, dividing are inverses. Squaring, square rooting are inverses. Inverse functions are two functions, not just operations, but functions that reverse the x and y values for input and output values. For example, what does that mean? There's a lot of language there, Mr. Close. I don't get it. For example, if I have a function and I input an x value for 3, I put it into my function and I get back this y value, negative 5. The inverse function says, we'll do the opposite. The inverse function says, if I put in an x value of negative 5, you should get back a y value of 3 because it's the opposite. Notice this 3 turned into 5, but here I've got this negative 5 turned into 3. Those are opposite functions. One gets you back to what you started with, oppositive. That's the opposite right there. That's what an inverse function is. The x and the y values are reversed. It gets me back to what I started with, and it just does the opposite sort of thing. If you want to find a function that's the inverse, then here's what we do. We're going to find the inverse of this function. This function f of x says take whatever x is, we're going to square it, multiply by 2, and subtract 10, and we'll get a value back. Now let's actually just put in, let's say x equals 1. We're going to find f of 1. In this case, we have 2 times 1 squared minus 10. And what do we get back? 1 squared is 1 times 2. That's 2. 2 minus 10 is negative 8. And so we have the point when x is 1, my y value is negative 8. But now let's find the inverse of that. The inverse should give me the opposite. If I put in negative 8 for x, I should get back to 1. But here's how you find the inverse. Step 1, take f of x and just replace it with y. So now we've got y. My y value is equal to 2x squared minus 10. There we go. We got x and we got y. The inverse function is we need to switch x and y around. So I'm going to rewrite it now as x equals 2 times y squared minus 10. This is what's going to make it an inverse. Remember, my inverse takes x and turns it into y. The inverse does the opposite. Y turns it back into x. So in the equation, we actually switch x and y around. Finally, now we can solve this for y to get y by itself. So let's add 10 to both sides. We've got x plus 10 equals 2 times y squared. Let's divide both sides by 2. So now we've got y squared equals x plus 10 over 2. And finally, we're going to square root both sides, and we end up with y is equal to the square root of x plus 10 divided by 2. Now let's just take a look about this, and I can rewrite this as my function, f of x, and it's the inverse, so we're going to put a little notation there saying that's the inverse of this function. This is f, this is the inverse of f, is equal to the square root of x plus 10 over 2. Now we can see a lot of these inverse operations, right? This one had a square, the inverse function has a square root. This one has a minus 10, the inverse function has a plus 10. This one had a multiply by 2, the inverse function has a divided by 2. So you can see all the inverse operations combined in this one inverse function. But now let's just finally check it out. Let's make sure our point actually works out. So if I put negative 8 in for this function, let's see if it actually gets us back to positive 1. All right, so we've got negative 8 plus 10. I'm putting negative 8 in for x divided by 2. What does that give me? Negative 8 plus 10 is 2. So that's the square root of 2 over 2. 2 divided by 2 is 1. So that equals the square root of 1, which is just 1. So look at that. In this function, when we put negative 8 in for x, we got back 1 for y value. And that truly is an inverse function, right? X and y values switched around. So that's how you find inverse functions. Again, to recap, take your function, put y in for f of x, switch your x and y variables around in the equation, and then solve it out for y, and then you end up with your inverse function. All right, there again, there's a recap if you want those notes on finding inverse functions as well. And we are done with week 12. What did we do? We did a lot with solving radical equations, finding solutions, being able to test if it's a real solution or an extraneous solution. And then we did combining functions, adding, subtracting, multiplying, dividing functions, and then talked about what composition of functions and a little bit with inverses. All right, great job. Good luck with all your week 12 assessments. Let me know if you need help with anything. And let's get this semester wrapped up.